In this lesson, we're going to learn how to identify and solve limiting reagent problems. When we are looking at a reaction and looking at stoichiometric amounts, what we mean is we have amounts of substances in proportion indicated by the balanced equation. For example, if we have one head, one middle, and one bottom of a snowman, then we can make one snowman. This will be considered a stoichiometric amount because we don't have any of our parts left over. The same thing would be true if we had two heads, two middles, and two bottoms. We could make two snowmen with none of our parts left over at the end. But what happens when we no longer have stoichiometric amounts of each reactant, or in this case, snowman parts? For example, if we have three heads, five middles, and four bottoms, how many snowmen can we make? We can only make three because we ran out of a part. We ran out of the heads, so we're done. Even though we still have middle and bottoms left over, we cannot make any more because we've run out of one of the parts. We are limited in how many we can make. And this is the idea of limiting and excess reagents. Reactants and reagents are two terms used interchangeably with one another. The limiting reactant is the one that's used up first in a reaction. Once it's gone, the reaction will stop because no more product can be formed without that particular reactant. The excess reagent or excess reactants are those that are present after all of the limiting reagent is consumed. With our snowman example, we see that the head is the limiting reactant. It is controlling how much of the product or how many snowmen we can make, while the middle and bottom are both excess reagents. We will have some of them left over after the reaction has stopped. How does this translate into a chemical reaction? The first thing we have to do is know how to recognize a limiting reagent problem. And in this case, what we're looking for is the amount of two different reactants. In this case, we have 25 grams of iron and 25 grams of oxygen. The amounts of two different reactants tell us that we're going to have to figure out which one is limiting the amount of product we can form. And we can't say, oh, there's no limiting reactant because they have the same mass. We have to always look at the amount of product that is formed from each of these substances. Before we start setting up our problem, I'm going to put our molar masses here above the reaction just as a reminder so we have them, because we know we're doing a stoichiometry problem, we're going to need those molar masses. The next thing we do on a limiting reactant problem is we assume that one of the reactants is the limiting reagent and that the other is in excess. And we're going to start by assuming iron is limiting, which means we're assuming that oxygen is the excess reagent. The first thing I need to do is start setting up my problem with my grams of iron because that's the amount I'm given. That's my starting point. I can use the molar mass of iron to convert to moles. Use my mole to mole ratio for my balanced chemical equation. So 4 moles of iron to 2 moles of Fe2O3. Now I can use the molar mass of Fe2O3 to find the mass of Fe2O3 produced if iron is my limiting reagent. Now we have to do a very similar calculation, only this time we're going to assume that oxygen is limiting and therefore iron is excess. As we did in the previous example, we're going to start with our 25 grams of oxygen. That was the amount given in the problem. We'll use our molar mass of oxygen to convert to moles. Then use our mole to mole ratio from our balanced chemical equation. So 3 moles of O2 to 2 moles of Fe2O3. Now we'll use the molar mass of Fe2O3 to find the mass of Fe2O3 that could be produced if oxygen was the limiting reagent. We see that when we assume that iron is limiting, the smaller mass of product was formed. Therefore, iron is our limiting reagent, and that is the correct assumption. We always have to look at which reactant will produce the least amount of product. Notice that we did two calculations here because we were given two amounts of reactants. If we had a different reaction and we're given 3 amounts of reactants, we would have had to do 3 calculations to determine which reactant limited the amount of product that could be formed. Since iron is our limiting reagent, we know that oxygen is our excess reagent. There will be oxygen left over at the end of this reaction. To solve limiting reagent problems, first, calculate the amount of product formed for each reactant given. We did that with assuming iron was limiting, then assumed oxygen was limiting. Then we look at the reactant which produces the least amount of product. That is our limiting reagent. We always have to look at the amount of product formed, not at the amount of the reactants. And then using whatever information we have along with whatever is being asked in the problem, we can then finish the problem. We cannot identify the limiting reagent by looking at the mass or moles of the reactant alone. We have to do the calculation to figure out which one is producing the least amount of product, because molar masses and molar ratios will play a role in determining that amount. Let's look through another example. If we assume that magnesium is the limiting reactant, how many grams of magnesium nitride can be made through the reaction of 35 grams of magnesium and 15 grams of nitrogen? Note that we are asking about only when magnesium is the limiting reactant. We can get our molar masses of our substances just so we have them for the calculations. But remember, we're only doing one calculation at this point. We start with our 35 grams of magnesium, use its molar mass to convert to moles, use our mole to mole ratio to get from moles of magnesium to moles of magnesium nitride, use our molar mass to get to grams of magnesium nitride, and we get 48.46 moles of magnesium nitride. We can ignore the small difference in the last digit. It resulted from different rounding, either intermediate rounding in a calculation step or slightly different rounding of a molar mass somewhere along the way. But we see that A is our correct answer. So if magnesium is limiting, the most we can make is 48.46 grams or 42 grams. Now we're going to do the same kind of problem, but we're going to assume that nitrogen is the limiting reactant. How many grams can we make? Again, this is only one calculation, so this is the other assumption for this problem. And we know it's a limiting reagent problem because it's given the amounts of two different reactants. I start with my 15 grams of nitrogen, convert to moles using the molar mass, using my mole to mole ratio, which is 1:1 from a balanced chemical equation, using the molar mass of magnesium nitride, and we find that we get 54.04 grams of magnesium nitride. Again, don't worry about slight differences in that last digit. So B is the correct answer. How many grams of magnesium nitride can be made through the reaction of 35 grams of magnesium and 15 grams of nitrogen? We've already done the two calculations to determine the mass based on assuming magnesium was limiting and then that nitrogen was limiting. And A is the correct answer, 48.42 grams, because that is the lesser amount. The smaller amount of product determines which substance is the limiting reactant. So always have to look at the product, and the mass of magnesium is greater than the mass of nitrogen, but the magnesium is limiting because we have to take into account we have different molar masses and different mole to mole ratios between different substances in the reaction, which ultimately impact the amount of product that can be formed.